Okay. So, we can now look into a little bit into the properties of the moist air and how you calculate out. Now, if you look at air, because the density would be needed all the time. So, we know that oxygen is around 20%, 21%. So, proportion by volume, and nitrogen, the molecular weight is this, argon is this much, and then carbon dioxide is this much. So, total overall molecular weight one can calculate out, right, proportion you know. So, therefore, it would come close to somewhere, it will come close to somewhere, it will come close to nitrogen. Actually, one can calculate this out, 32 into, for example, 32 into 0.2095 plus 28 into etcetera, etcetera, if you calculate out. So, molecular weight of air one can obtain. Now, I was just mentioning you the processes. So, you can see the processes in a psychrometric chart like this. So, this is dry bulb temperature, this is your moisture content. Now, what you know the processes, for example, this we call, when I am just simply keeping the moisture content same and I am heating it, I call it sensible heating. There is no latent heat exchange occurring. So, we call it sensible heating, and this obviously the other side, this is the initial condition. If I am going along this direction, I call it sensible cooling, sensible cooling. So, moisture content is not changing, right. Now, this is basically after beyond this point, this will be condensation, right. This will be this here the this dew point condensation would occur, and then this, if I am going vertically upward, I am increasing the moisture content at a constant temperature. So, I call it isothermal humidification, isothermal humidification. This is isothermal dehumidification, isothermal dehumidification. Now, supposing I am cooling it, say example is a desert cooler. Now, in desert cooler what happens? Air enters through a filter, and where water percolating, water is percolating, water percolates from top, right. So, air enters in this manner, and it is dry air, usually it is effective only in dry summer. Desert cooler is not effective in country. Yeah. So, the coastal area of India desert cooler actually does not work, while northern India or Rajasthan, etc., it still works. So, because the air is dry, sufficiently dry during hot summer, and what happens is as the moisture enters, air enters this way, it absorbs some moisture from liquid state to the vapor state. Now, to vaporize it needs heat, it absorbs that heat from the hot air itself. So, this is a process where you are not supplying any heat from outside, but there is a change, it takes the heat from inside itself and gets cooled. So, that is a adiabatic process. So, that is actually it is adiabatic humidification. That is what happens in case of a desert cooler. It increases its moisture content, loses its own heat. So, therefore, there is a reduction in the temperature. So, this is adiabatic humidification, adiabatic humidification. Similarly, supposing I pass it over, there can be chemical moisture absorption. I can spray of course moisture straight away, but if it is the same temperature, there is no problem. Same temperature if I am maintaining, then it is actually if I this will be isothermal isothermal humidification if I am right. But supposing this I said that adiabatic humidification I said. Now, supposing I pass it through a bed which can absorb moisture, kind of a desiccant, pass it through a desiccant, right. As I pass it through a desiccant, the moisture from the air will be absorbed by the desiccant, right, it will be absorbed by the desiccant. So, if the desiccant absorbs it and temperature do not change, temperature is maintained constant, then obviously it will be isothermal dehumidification. But chemical dehumidification also there is an increase in temperature, because you are if you basically if you are taking out the moisture vapor, so some amount of latent heat exchange is also occurring, and that that can cause increase in temperature. So, that is chemical dehumidification. Chemical dehumidification is this, sensible. So, you can explain all the processes in a psychrometric chart like this, right. Okay. So, this is what I mentioned you earlier, and then let us look at this one. Now, this is again in the psychrometric chart. I have got a moisture content, and I have got the dry bulb temperature here, and this is my point. So, what I said is, if I mix it, the law of mixture follows. What I am doing, my process would be, I have some fresh air and some recirculated air, and I am mixing them and each of them are at different temperature. So, if the mass of one of them say is m1, let us say recirculated air is m1, and mass rate, I am talking of mass rate only, in kg per second, and mixing, I am mixing them m2, and this is at temperature T1 and this is at temperature T2. Then after mixing in the duct, my rate now would be m1 plus m2, and since there is no loss in temperature, this multiplied by final temperature T, which is the mixture temperature, must be equals to m1 plus T1 plus m2 plus T2. So, basically mass flow rate would increase, m will be given by, now my mass of the mixture will be m1 plus m2, mass flow rate of the mixture will be m1 plus m2, and its temperature. So, if these two I am mixing, if I am mixing at two different temperature, we can show that it is linear, but let us look at the algebraic part first. So, it is something like this, the mass will be m1 plus m2, the temperature would be m1 plus T1, temperature will be given as m1 T1 plus m2 T2 is equals to mt mixture, or T if I may call it simply. Similarly, the moisture content will be given as m1 G1 plus m2 G2 is equals to mg, and similar also specific enthalpy. So, law of mixture follows, and you can see that simply this one can write this like this, m1, if I have this expression, simply I can write it in this manner, I can write it in this manner, simply I can write it in this manner. Okay. For example, I said this is the relationship. So, m1 T1 plus m2 T2 is equals to m1 T plus m2 T, right. T is the final temperature of the mixture. So, I can bring it on one side, m1 T1 minus T is equals to m2 T minus T2, or same thing I can do for G. So, you can see that m1 G1 minus G is equals to m2 G minus G2. The ratio of m1 by m2, so the change in moisture content or change in temperature, ratio of change in temperature is kind of inversely related to rate of heat diffusion. For example, m1 and G1 minus G, m2 G by G minus G2. So, this can be expressed again, this can be explained in a psychrometric chart like this. For example, this is point A, point 2. Now, temperature, this would be m2, m1, supposing this one is T1, this is T2, right, T2. So, the proportional, it would change accordingly, because as you can see that T minus T1, T minus T1 or T minus T2, this similar triangle, these two similar triangles are similar, so T minus T is this, T minus T1 divided by M1 must be equals to T2 minus T divided by M2, T2 minus T divided by M2, you know. So this relationship for G or T or anything H, it is valid actually. M2 by M1 is equals to G1 by G divided by G minus G2. So it can, one can express this in psychrometric chart also, but does not matter, we just for this, for the sake of explanation, because today we will generally be calculating this very simply from the equations given. So supposing I tell you the rate, because one of them say fresh air supply I need from hygienic condition. Now my this T, if I have fixed my supply air temperature differential, then T2 also would be known to me, you know. So finally the how much will be the fresh air supply, you know, I can using these equations I can calculate this out. So we will do this as an example, but just let's go back to this. So that's, you know, that's one on the psychrometric chart, all this kind of this thing you can explain for, or you can represent them, but for our understanding or calculation purpose we will simply use the algebraic equations. So, okay, so that is number one. Number two is, issue is, as I said, sensible heat removal is given by mass flow rate into specific heat into room temperature minus supply temperature, and latent heat removal is the same mass flow rate Gr minus Gs into latent heat. Now mass is nothing but rho into volume. Now rho itself is a function of temperature, rho itself is a function of temperature, and what we do, we know that at 20 degrees centigrade, rho at 20 degrees centigrade is 1.2 kg per meter cube, and we know that rho 1, no, this is rho 1 T1 is equals to rho 2 T2 from ideal gas law, rho 1 T1 is equals to rho 2 T2, right. Okay. So therefore this is 20 degrees centigrade 1.2 multiplied by 273 plus 20 is equals to rho 2 into whatever the T is, the 273 plus, you know, this is all in absolute temperature. So 273 into whatever my T is. So this, therefore what we do is 1.2, Q is the flow rate, let us say, not V, we are not using V here, Q is the flow rate, into 293 divided by 273 plus supply air temperature, right. This is latent heat, this is latent heat of evaporation of moisture is 2501, and this is the moisture content minus the room moisture content minus the supply moisture content. So this is, this QL latent heat transfer is given by this formula, because latent heat transfer is mass flow rate into L into delta G, mass flow rate into delta G into L. Sensible heat will be mass into specific heat into Tr minus Ts, and which you can write as 1 minus same, you know, density part of it into the Q flow rate into Ts minus Tr, whatever it is, and well, depending upon, I mean, it should be Tr minus Ts only. There is no, you know, Ts, because Tr will be always higher. So this will be Tr minus Ts. I mean, you want to, absolute value of that has to be taken anyway, Tr minus Ts, and specific heat is given by 1.024, specific heat is taken to be 1.024, right. So this is the density, this is a, you know, Q is the volume, and the specific heat into Tr minus Ts. So that's what it is, that's what it is. Now there are two equations available to me. First of all, for a given room, supposing I have any room or any space basically, what will contribute to the latent heat? I mean sorry sensible heat, the heat coming from outside, heat coming from outside, fabric heat gain. So, what we call as fabric heat gain, fabric heat gain. And we have elaborate ways of calculating this, but in this class we are not doing that. Okay. So, we have elaborate way of calculating this, because this would involve like if you are looking only at the capacity. So, I will consider the peak situation, peak heat, but otherwise it varies from time to time of the day, and fabric heat gain, because solar radiation outside would change, temperature outside would change. So, one has to, depending upon the location that you are dealing with, say Delhi or other place, and every orientation of the walls, roof, etc. So, many is fairly elaborate process, but for our purpose here we take the design fabric heat gain, for which I am designing the system, right, for which I am designing the system. So, fabric heat gain is one issue. Then there is casual heat gain. Casual heat gain would come from appliances inside. So, one is fabric heat gain, two is a casual heat gain which will come from the appliances and people inside, people etc. So, casual heat gain would be this, casual heat gain. So, all this heat gain, some of them might have sensible heat gain. For example, fabric heat gain is largely sensible heat gain, right, temperature changes related. Sensible heat gain is related to temperature changes, but casual heat gain, some of it could be even latent heat gain. How? Because perspiration from the human body generates moisture and that is to be removed. So, that is absorbed by the supply air. So, there is a latent heat changes. Similarly, supposing I am working in a space where there is chances of some for example, it is a laboratory and temperature is to be maintained, there are some processes where moisture is evaporated. So, that would also contribute to the latent heat, because you will remove that much amount of moisture vapor, that much corresponding latent heat you are removing, or a restaurant or kitchen. So, there the some the latent heat also is removed. So, we remove both latent heat as well as sensible heat. Now, what we do is we find out which one is higher. First we calculate this. Now, calculation is fabric heat gain, casual heat gain coming from appliances and human being, occupant etc., etc. So, this total we sum up, right, rate of heat gain we sum up actually, and also both separately we do, and we now find out whichever one is higher. Supposing this is higher, sensible heat gain is higher, which is the case usually, or let us say latent heat is higher. Now, let us say sensible heat gain is higher, then what we do? We have to decide upon this based on the principle that I mentioned earlier. What is that principle? Because if you make this too large, if this differential is too large, then your insulation required will be more. So, cost of insulation will increase, and if you keep it too low, then this has to be higher. So, duct sizes will increase, and if you want to keep the duct size lower, the velocity will then increase, the noise could be there. So, based on this is by and large fixed. We first decide that okay, we will keep a 10-degree differential or 8-degree differential, some differential we fix it up. Once I have fixed it up, this is what I have calculated from fabric heat gain etc., etc., sensible and latent heat gain, I mean sensible heat gain from fabric, or otherwise from casual heat gain. So, in that case I have calculated this is known to me, this I have decided, this I have, of course I can't do anything, this is already the it's related to the air itself. So, I can find out the flow rate, mass flow rate I can find out. Now, for this given mass flow rate is now fixed, and I would like to know what is my GR. GR is also known because relative humidity inside the room is known. So, when relative humidity inside the room is known, from the known relative humidity corresponding moisture content I can find out, either using psychrometric chart or using some equations. either using psychrometric chart or using some equations, right. I can find out these GR values, I can find out these GR values. So, moisture content within the room will be known, and then how much I want to remove, because GS would depend upon, GS, if GR and GS is same, no moisture will be removed. So, latent heat to be removed, I calculated it out, because casual heat gain might result in some requirement of latent heat removal. So, latent heat, how much I want to remove, that I know. M has been already fixed, GR is known, what should be the value of GS, that then I can find out. So, first step is calculate out the sensible heat gain and latent heat gain. Some information must be available to you. For example, how much is the fabric heat gain, that has to be known to you, for which you are designing fixed value, not changing, fixed value, because your duct etc., is fixed for a given value. So, fabric heat gain, what is the possibility of fabric heat gain, that you would like to know, for which you are designing, and then what are the function of the room. For example, knowing the function, you can find out how much will be the casual heat gain. Say if we consider a classroom, it might be operating, let us say 80% population is full. So, 80% means the class capacity, let us say, is 60. So, about 50 you might design for 50 full, right. So, because you take an even diversity factor you can take into account, might design for something like 50 or something of that kind, and then for that many persons, how much you can expect the moisture perspiration from per person, that is known, and therefore, that much latent heat is to be removed, that you can find out. So, we will do an example calculation and we will see for a restaurant case. So, you can find out how much latent heat you want to remove, and if there are 50 people, there will be metabolic heat gain from each person, sensible heat gain from each person. So, fabric heat gain capacity, a peak fabric heat gain, you know at this design condition what will be the heat coming from people, etc., total heat to be taken out, sensible heat to be taken out, and latent heat to be taken out, you can find out. Once you have done that, this being known, rate you can find out. Rate is known, moisture content you can find out, because this is known. So, that is what it is. So, this is this is what would be our exercise, this is what would be our exercise. But there is one issue, of course, we must take into account, is that there is something called, you see, you have supply air coming in from outlet of the duct, but then its whole room temperature could be quite different than near the duct temperature, right. So, there is something called contact factor. Contact factor is the efficiency of the heat transfer mechanically from radiating surface. This is more important for heating actually, because there the radiating surfaces near the surface temperature is pretty high, room temperature is lower, and alpha is what is called contact factor, beta is bypass factor. So, sum total of these two is equals to 1. Contact factor is given as supply temperature minus the room temperature, right, okay, and average room temperature and supply temperature. This is the room temperature, and this is near the duct itself, near the duct itself. Yeah, because this is the bypass factor, this is the amount that is bypassing. This is the amount supply, this is just a minute, because this is the amount which is bypassing. That means this is not available to me. What I am getting is yeah, this is right. So, this is what is T is the room temperature. If it is a heating system, cooling system, this will be lower, this will be higher in fact near the surface. If it is a heating system, room temperature would be in all cases, no, it is a cooling system. If it is a cooling system, this would be higher, and this would be this would be higher, this will be lower. Yeah, that's right. So in a cooling system, this will be higher, this will be lower. Near the duct, this is what it is. So T is room temperature is higher than the near surface temperature. So this is what is the bypass. This is what is the bypass. Actually, this is what is the bypass factor. Sum total of this is equals to 1. Sum total of this is equals to 1. Actually, it should have been same. Supply air temperature should have been, or near to the, I mean the basically the near the duct and room, that should have been same actually. Here there is a difference. So this difference, this is contact factor, this is called, one of them is the bypass factor. Sum total of this is actually equals to 1. So if I sum up, actually T gets cancelled, Ts minus T1, yeah, that's what it is. So one is bypass factor, means that's not available, that's that's going out. So that's what it is. So that's right. That's some of those two issues, separate issues just I discussed. Now summing it up then, design of air quantity, what I mentioned earlier, I am just again summing it up. Air quantity is a compromise between temperature differential and quantity of flow. Noise and size of the piping limits Q, right? Quantity of flow, because if you want to increase Q, either size you will have to increase or velocity you will have to increase. So therefore, noise and size of piping restricts Q, limits Q, while efficiency of distribution limits temperature differential, right? Efficiency of the distribution means insulation required. Losses should be higher. Losses should be higher. If the supply air is if you cool it to a lower temperature, the tendency of losses it would be higher, because rate of heating, not from the surrounding, absorption of heat from the surrounding. If the temperature is low, it will tend to absorb more heat. So this is what it is. So this is what dictates. Sensible heat ratio is basically ratio of sensible heat to total heat removal. For example, Qs divided by Qs plus QL. How much proportion of the total heat removed is this much. So this can fix the slope of the whole thing. Okay, obtain the slope of a room supply line, right? So then this is basically the guideline. I mean idea why we why and how we keep the temperature differential fixed, and then why you keep the temperature differential fixed first to find out the flow rate, and then estimate basically the temperature, supply temperature and supply moisture content. Okay, so let's see now how it looks in a psychrometric chart again. So it's something like this. Let us say this is let us say outside air temperature. This point in a psychrometric chart, this is absolute humidity, moisture content, this dry bulb temperature. Therefore, outside air I can represent in a psychrometric chart. So this is the moisture content of the outside air, this is the temperature, this is the outside air, right? Now room air is somewhere here, room air is somewhere here, right? So room air is somewhere here, this is the room air, and then I mix them up in some proportion. I would like to keep the fresh air requirement to a minimal, because I mean room air, outside air, that is the fresh air required to a minimal. Why? Because if I keep it high, my cooling cost will increase. Like to maximize recirculated air. Now, but there is a minimum requirement. Minimum comes from hygienic condition. So therefore, I mix up, and mixture temperature will be somewhere there, because it will be between T1 and T2 depending upon the proportion that I am mixing, that by that formula that we have talked about. So M1 by M2 is equals to, it was T minus T1 and T2 minus T, something like this. Yeah. So you can see that it would depend upon, so it will be somewhere in between. I can join them by a line and it will be somewhere in between. So this means, you know, that from similar triangle, this will be my M2 or proportion of the relative proportion of the or amount of recirculated air, and this is the amount of fresh air, because you know inversely proportional as you have seen. So finally somewhere in between, the temperature will be somewhere in between, right, temperature. So temperature will be somewhere in between, and G also will be somewhere in between. Now then what I do, I cool it to a temperature much lower than the room temperature. Cool it to a temperature much lower than the room temperature, and if required I might cool it and heat it also a little bit to control the moisture content. So I might go somewhere there where there will be some amount of condensation as well, maybe if it is reaching the dew point. But if the condensation is not required, I will simply, this is the supply air temperature and moisture content, then it will come, it will do, you know, it will absorb this much of, so this is the amount of this, you know, it absorbs this much of heat. So it will have two components. The horizontal component will talk about the sensible delta T changes, correspondingly there will be some sensible heat removal. There was a vertical absorption of moisture, so there will be some latent heat removal as well. So that is why, you know, so if it is straight line, then sensible heat gain, the air will have some sensible heat gain and it will have some latent heat gain also. So that is the process actually. So supply air is somewhere there. There will be some losses, you might have to take care of some of the losses in the duct. So supply air temperature may be still lower because you take care of the losses in the duct. So losses in the duct, so that is how one can, you know, this is the process is something like this. So what we will do is, in the next class we will look into this is a same thing, it is being shown what I showed earlier, and then we will take up an example case and solve. You know, this is a problem of an example case actually, where we have fresh air supply is given, then you have got recirculated air, right, from the room it is coming, they get mixed up, there are dampers and filter, and then there is reheating, winter heating, and then there is cooling and air heater, etc., etc. So that is what it is, all right. So we will look into that in the next class.